All right, welcome to The Explainer. Today we're going to tackle one of the most notorious and frankly most misunderstood parts of Python, the global interpreter lock. You've probably heard of it, the GIL.
So here's how we're going to break this down. First, we're going to look at a really weird multi-threading mystery in Python. Then, we'll meet the culprit, the GIL itself. After that, we'll get into a crucial distinction between different kinds of tasks, and then we'll cover how to get around the GIL, from the standard ways to some more advanced methods. And finally, we'll wrap up with how you can choose the right tool for your specific job. All right, let's kick things off with a real head-scratcher, a paradox that honestly trips up a ton of Python developers. Picture this. You've got a really heavy, time-consuming task. The logical thing to do is throw more threads at it to speed it up, right? But in Python, it often doesn't get faster. Sometimes, believe it or not, it actually gets slower. Okay, let's look at a concrete example. Say you're running a really CPU-heavy task, something like calculating a huge Fibonacci number. On a single thread, it takes, let's say, about 7 seconds. Now, you'd think, I've got a quad-core machine, I'll use 4 threads, and it'll be way faster. But nope. Look at this. The execution time actually goes up to around 9.5 seconds. It's totally counterintuitive. It goes against everything we think we know about parallel programming. And if we peek under the hood at the CPU usage, it gets even weirder. You might expect one core to be pegged at 100%, or maybe all 4 firing on all cylinders. But what you actually see is each core just kind of puttering along at 25%. It's like instead of having 4 people working on a project at the same time, you have 4 people standing in a single file line, each taking a tiny turn before getting back in line. They're just fighting for the same resource instead of working together. So this all brings us to the big question, right? We have all this powerful hardware, multiple cores, multiple threads. So why isn't Python using it? Why does it act like it can only do one thing at a time? Well, the answer, and the culprit behind this whole mystery, is a single fundamental piece of the standard Python interpreter, CPython. It's called the Global Interpreter Lock. You'll hear it called the GIL. So what is the GIL? At its core, it's basically a lock. Think of it like a token or a key. And in any single Python process, there's only one of these keys. A thread has to hold that key to execute any Python code, which means only one thread can run at a time, period. You could have a supercomputer with 64 cores, but if you're running a multi-threaded Python program, only one of those cores will be executing your Python code at any given instant. Now, you might be thinking, why on earth would they design it this way? And that's a fair question, but it wasn't an accident. It was a very practical design decision way back in the early days of Python. You see, the GIL made managing memory much, much simpler and safer. And maybe most importantly, it made it super easy to integrate with existing C libraries, which was a huge reason for Python's early success. So if it's such a bottleneck, why not just get rid of it? Well, people have tried for decades. But it's turned out to be incredibly hard. And this quote from Guido van Rossum, Python's creator, really gets to the heart of the problem. The non-negotiable rule has always been, whatever you do, you cannot make single-threaded programs slower. And since the vast majority of Python code out there is single-threaded, that's a really high bar to clear. Okay, so at this point, it sounds like Python threads are pretty much useless for performance, right? Well, hold on. This is where the story gets really interesting. Because it turns out the GIL doesn't mean threads are always bad. In fact, for certain kinds of tasks, they're fantastic. It all comes down to what your code is actually doing. You really need to understand the difference between 2 types of work. First, you have CPU-bound tasks. These are the number crunchers. They're all about pure computation. Our Fibonacci example was a perfect case of this. Then you have I/O-bound tasks. I/O stands for input-output. These tasks spend most of their time just waiting for a website to respond, waiting to read a big file from the hard drive. The CPU isn't doing much at all. It's just twiddling its thumbs. And here is the absolute key to everything. This is the secret. When a Python thread is doing one of those I/O-bound tasks, when it's just sitting there waiting, it does something very polite. It releases the GIL. It puts the key back on the table. This means another thread can swoop in, grab the key, and start doing its own work. So for tasks that involve a lot of waiting, threads can provide a massive speed up through concurrency. Okay, so that's great for I/O tasks. But what about our original problem? What if your task really is a heavy CPU-bound calculation? How do you break free from the GIL and actually use all those cores you paid for? Well, thankfully, Python has a built-in, officially recommended solution for exactly this scenario. And that solution is the multiprocessing module. The concept is pretty simple. Instead of creating multiple threads inside one Python process, you create multiple processes. Each new process is like a whole separate Python program. It gets its own memory space, its own Python interpreter, and crucially, its own GIL. And the best part, look at the code, the way you use it is almost identical to the threading module. And the results? They speak for themselves. Let's go back to that Fibonacci task that took over 9 seconds with threads. When we run it with 4 times processes instead, the real time it takes you to get an answer drops to just over 2 seconds. That's a huge speed up. We've achieved true parallelism by sidestepping the GIL entirely. But of course, there's no free lunch. Multiprocessing isn't a magic bullet. For one, starting up a whole new process takes more time and memory than starting a lightweight thread. The bigger issue, though, is communication. Since these processes don't share memory, if you need to send data from one to another, Python has to package it up, a process called pickling, send it over, and then unpack it. That overhead can really slow you down. So, multitasking is the standard answer. But what if you need even more performance, or if the overhead is too much for your use case? Well, then you can dive into some of the more advanced techniques for getting around the GIL. A common approach is to use libraries like NumPy or Pandas. The magic here is that all the heavy-duty math is happening in highly optimized C code, underneath, and that code can run on multiple cores. Other options include switching to a different Python interpreter entirely, or, for the truly brave, writing your own C code extensions and manually managing the GIL yourself. Okay, we've covered a lot of ground, so let's bring it all together. What's the bottom line? How do you decide what to use? It really boils down to this simple strategy. Step 1, and this is the most important step, figure out what kind of problem you have. Is your code spending its time computing, or is it spending its time waiting? If you're waiting a lot, for networks, for disks, then use the threading module. It's lightweight and perfect for that job. But if you're doing heavy-duty computation, if you're CPU-bound, then reach for the multiprocessing module. That's how you'll unlock true parallel performance. And I'll leave you with this one last thought to chew on. For decades, this has been the reality of Python concurrency. But that might be about to change. There's a really exciting proposal on the table right now, PEP 703, which aims to make the GIL optional in future versions of Python. If that effort succeeds, this entire conversation we just had could become a footnote in Python's history. The entire game could be about to change.